Okay, I mentioned we have all the tools to solve interesting forced harmonic oscillators, but we don't have the muscles yet. So we're going to build those muscles here with a little warm-up. Specifically, I'm going to give you a problem that you already know how to solve that we've really beaten to death a little bit. But solve this forced harmonic oscillator, y double dot plus 4y equals 3 cosine of t, with the initial conditions that the initial position and the initial velocity are both 0. So this, this is a forced harmonic oscillator with no damping. Maybe it's on a table that's tilting with a period of 2 pi. And the spring or the mass is initially at rest at the, wherever the spring naturally rests, and it has no initial velocity as well. And then, so it's just the tilting table that moves the spring. And we know how to solve this, right? Like we can solve this in our sleep at this point. We solve the homogeneous version. That's very, very easy. And then we know that a particular solution is actually just going to look like a cosine of t because there's no y prime term or y dot term. So we don't need to use undetermined coefficients for cosine and sine. We know it's just going to have a cosine. We could complexify this differential equation and solve it that way to find a particular solution, knowing that the real part of our complex solution to the complex differential equation will be what we need as the solution to this. So we've really solved this. Okay, we really solved this. But this is what we're going to use. We're going to use something we're comfortable with to model how we're going to apply Laplace transforms. And that's what this video is all about. Later in the section and all in the next section, we're going to deal with more complicated situations. We're just getting practice right now. How does it work? What are the good steps to be going through? And the first thing to model in solving a differential equations is we want to do some brief qualitative analysis. One of the best examples, or one of the best things about having physical systems, is we have some sort of expectation of how they should behave. And if we can get an expectation of what our solution should look like, then when we get our solution, we can do a quick check and say, does this solution actually make sense? So we always are going to start all this section and all the next section by some brief qualitative analysis. So we know we can find the natural frequency very easily, or the natural period, whichever quantity we might be interested in. They're just reciprocals of each other because the homogeneous solution has eigenvalues of just plus or minus 2i. All right, so that tells us that our natural period is just pi. Right, because we're going to have a cosine of 2t in there. So period's 2 pi over that 2, period's just pi. The natural frequency is its reciprocal, 1 over pi. And we know that the forcing period is 2 pi. Right, the period of the forcing function is just 2 pi. So that immediately tells us something. We have an undamped harmonic oscillator. The natural period and the forcing period are quite different, although they are multiples of each other. Does that do anything? We'll look at it. So there's no resonance, okay? And that's very important. Anytime you're looking at a very, very underdamped or an undamped harmonic oscillator, you should always be thinking about, are we getting resonance? That's very, very important to think about. And we're not. Okay, so those are the main things. Our solution's just going to be some kind of sum of sines and cosines with periods 2 pi and pi, and we're not going to get anything crazy. And furthermore, these aren't very close to each other, so we're not expecting to see a lot of beats. So now that we have an idea of how our solution is going to behave, let's solve the problem with Laplace transforms. Okay, so we'll solve it with Laplace transforms, and we are going to take the Laplace transform of both sides. So really what we're doing is taking the Laplace transform of the left-hand side and the Laplace transform of the right-hand side. But again, because it's linear, we are able to break it up. So we're going to get the Laplace transform of y double dot plus 4 times the Laplace transform of y equals 3 times the Laplace transform of cosine of t. Now we can work with all of this. So you have the tools already. This is a warm-up problem. Pause the video right now. Use your formula sheet to evaluate all of these Laplace transforms, and then undo the Laplace transform to get your solution. And remember, we will have to use these initial conditions. All right, so hopefully you paused the video and got to the answer. I'll walk you through the solution to see what it looks like. Remember, this is just s times the Laplace transform of y dot minus the initial condition at y dot. This is 4 times L of y. We can't do anything with that. We don't know what y is yet. And equals 3 times the Laplace transform of cosine of 1t. The Laplace transform of cosine of 1t is 1 over s squared plus 1. And then we need to deal with this some more. This is going to be, I'm going to distribute this. This is s squared L of y minus s times the initial condition, which is 0. Right. I just used this property again and distributed the s. And then y dot of 0 we did say was 0. So these are the same thing. Plus 4 Laplace transform of y, we do not know that. And the right-hand side we could rewrite a little bit. We need to solve for the Laplace transform of y so we can undo it with the inverse Laplace transform. We do that by factoring it out. We're left with an s squared, as we often will be, plus 4. We get 3 over s squared plus 1. And we find out that the Laplace transform of y needs to be 3 divided by s squared plus 1, s squared plus 4. We are not done. It's algebra time. Because we don't really care about what the Laplace transform is. We want to know what y is. So of course y is going to be the inverse Laplace transform of this. Oh. Do we have anything with 2 quadratics multiplied by each other? No, we don't have anything with 2 quadratics multiplied by each other unless, and we haven't introduced this property yet, unless it's the same quadratic, and then we have a property. So none of these will help us. And remember, we can't split this up into f times g, because I just told you, when did I do that? I just told you this is bad. So what are we going to do? We can't factor either. We're going to use partial fractions. Okay? So we're going to go off to the side and use partial fractions. What is this? We're going to say, okay, 3 over s squared plus 1 times s squared plus 4 is going to be some constant. Oh, not just some constant. Remember, if there's a quadratic in the denominator, it makes your partial fractions more exciting. Hooray, we get something more exciting. It's some linear term in the numerator over s squared plus 1, plus another linear term over the other one, s squared plus 4. Oh boy. Also, it's s, not x. So this is fun. And again, we'll go through this quickly. As a reminder, I do have videos linked for how to do partial fraction decomposition if you need to review. A quick Google search will give you tons of videos and pages in practice too. But we'll quickly go through this to remind you all of how it's done. We'll multiply both sides by the least common denominator, just like we did before. That'll give us as plus b times s squared plus 4 plus cs plus d times s squared plus 1. And there's a few ways that you can solve this. You could match your coefficients, or you could plug in complex numbers. I like plugging in complex numbers, and we've been doing a lot with complex numbers, so why not? What if s is 2i? What do we get? We get 3. Oh, 2i, this becomes negative 4. This all goes away. And this becomes s is 2i, so this is 2ci plus d, and this becomes negative 4 or negative 3. Divide both sides by negative 3, we get negative 1 equals 2ci plus d. How do you have a complex number equal a real number? The imaginary part better be 0. So c must be 0. And what does d have to be? -1. And then we do the same process. Again, great opportunity to pause the video. What else could we plug in? What is a and b going to be? All right, we are going to plug in I. And we do that, we get that 3 needs to equal, this becomes a times I plus b. This becomes I squared, which is -1. Plug in I, this whole thing is 0. And similarly, we get 3. Oh, sorry, we divide both sides by 3. We'll get ai plus b is 1. So we get that a has to equal 0 and b has to equal 1. Great. I did not make a lot of checkpoints for me along the way, so it'll be really embarrassing if I made a small mistake somewhere. But we could check our answer if we wanted to. So we're going to get that y of t is the inverse Laplace transform of all of this, which we just found. It's going to be the inverse Laplace transform of as plus b. Oh, that's nice. That's just 1 over s squared plus 1. Plus cs plus d. Oh, nice. That's just going to be a minus 1 over s squared plus 4. This is great. And again, how would I check? I would just, to check partial fractions is way easier than doing partial fractions. You check partial fractions by just combining the fractions. This gives us s squared plus 4 minus s squared minus 1 when you distribute it. The s squareds cancel, and you get 4 minus 1 is 3. So we did do our partial fractions right. Remember, that's a quick check. Just combine these, and you can check whether you did it right. Okay, so we have these quadratics in the denominator, s squareds plus omega squareds. What does that look like again? S squared plus omega squared looks like sine. They both seem to be the same form. Okay, so again, Laplace transforms linear. We can do them both. This right here is already in the right form, where omega is 1. Again, using this property. So this first one is just omega over s squared plus omega squared, sine of omega t. This first one is just sine of omega t. Minus the second one needs a little bit more work, right? Because here omega is 2. All right, we've done that before. We know what that's going to look like. We need a 2 in the numerator, so we just multiply by half. And again, we get sine of omega t, like so. So remember when I said it'd be really embarrassing if I made a really small mistake a long time ago and kept doing the whole problem? The Laplace transform of cosine is s on the top, not omega. What I was doing is I was looking at the Laplace transform of sine, which has the omega on top. Laplace transform of cosine has the s on top. So what we are going to do instead is we're going to rewrite history. Let's say that we were solving this equation. All right. Then everything else still holds, and it's just as meaningful, I think. So if we do that, then we're at a pretty good spot right here with the solution. And we could check our solution if hypothetically we were worried that we made another mistake by saying, okay, well, what is y prime? Again, this is our solution right here. We can check our solution by saying, what is y prime? It's going to be cosine of t minus cosine of 2t. And y double prime is going to be negative sine of t, and then plus 2 sine 2t. It needs to satisfy the differential equation y double dot plus 4y. So y double dot plus 4 of this, what is that going to get? This plus 4 of this, it's going to give us 3 sine of t this plus 4 this is going to cancel each other out, plus 0, and that indeed equals 3 sine of t. And does it check out the initial conditions of initial position and velocity being 0? Plug in 0, you get 0. Yep. Plug in 0 into this, and you also get 0. So this is indeed our solution to a slightly different differential equation than I originally wanted to give you. My apologies for that oversight. Okay. Now, what we can do really quickly is we can graph this and see whether our qualitative behavior is satisfied. Right? We said there should be a natural period of pi. We said that should be different from the period of the forcing function. We said there's no resonance. And again, this is all much the same, whether it's sine or cosine. In fact, the original answer, if you did do the problem by yourself, the original answer was y of t equals cosine of t minus cosine of 2t. So very, very similar answer if you don't write the problem down wrong. All right. So this is the answer to the original problem. And when we look at that on Desmos, we can see our qualitative behavior is pretty much right. There is no resonance. There is no beating. I mean, you could say this is some kind of beating, but certainly it's not like it would be very short beat frequencies. All right. And we can see again that initial position is 0 and the slope of our initial function is 0 as well. And so, yeah, all of our behavior is good. We got some practice using partial fractions. We introduced how to use Laplace transforms. Make sure you're looking at the right one between sine and cosine. And remember, this is just a warm-up. We could have solved this much quicker, much easier using techniques that we've already learned. But the point of doing it this way is to practice doing Laplace transforms on easier differential equations so that, I believe, in the next video, we'll start doing discontinuous forcing functions. And that'll lead us to some really cool things so that by the end of 6.4, which is our last section, by the end of 6.4, we are going to do something extremely cool. All right. So that's coming up. Let me know if you have any questions. Have a good one.